So now we're looking at past paper questions relevant to the ideas that we've studied yet, related to just simple magnetism, because what we'll be starting next are ideas related to electromagnetism. So basically this is where it is till simple magnetism. Now may I warn you that you might not see a lot of questions just related to simple magnetism, because what is usually assessed more are ideas related to the magnetism and electromagnetism unit as a whole. So let's just do the questions that we can. Let's start off with some MCQs. This question is from Winter 22, paper 1-1, question 26. Again, pause this video to see if you can get through this on your own, or otherwise continue watching to see how it's done. 4 plotting compasses are placed near a bar magnet. Ignore any effects of the Earth's magnetic field. One compass appears like this. What is a possible position for this compass? Now I know that how the field lines are going to be. They are going to be like this, from north to south, like this, and then similarly like this here. And then if I want to link it up with this one, it's probably going to point something like this. And it says that the compass appears like this. Now at this position, right in the middle of the magnet, this is going to appear purely to the left. So is D, and B is going to appear to the right. And now for C, it depends on how I shape my field lines, because I can see this would point somewhat like this. Then I can say this is still pointing vertically downwards as compared to the other two. That's why C is going to be the correct option to this one. Let's have a look at another one. This one is Winter 18, paper 1-2, question number 28. Which diagram shows the magnetic field in the region between the N poles of two magnets? So between N poles, I know that, for example, the north pole is going to be somewhere here. It's going to be equally pulled. It's equally going to be repelled by both of these. So in the middle, I should have a null point. So no field lines there. So it cannot be C or D. And I know that this is what the field line patterns look like. And additionally, the field lines must be going away from the north, which is happening here and here, but not here, because these are coming into north. So A is also wrong, and B is my correct answer here. Let's go on to structured questions. So this is one of those structured questions. This is Summer 22, paper 22, question number 6. Now the actual question is lengthier than this, but right now, because we have not done all of the syllabus content regarding electromagnetism, so we can't do the other part. But this is something we can do. 6.1 shows part of a toy which contains 2 ring-shaped permanent magnets. A plastic rod passes through the center of both. Top magnet can move up and down freely along the plastic rod. The magnetic poles on the bottom magnet are shown. The top magnet floats in the air above the bottom magnet. On 6.1, mark the poles on the top magnet and explain why it floats in the air above the bottom magnet. So for this to float, and if this is not falling down, this must mean that this bottom magnet must be repelling this one. And this is why it remains suspended like this. So I know that for repulsion to happen, the poles at the bottom must be north, and the poles at the top must be south poles. So then I need to explain why this is going to happen. So on 6.1, I've marked the poles, explain why it floats in the air above the bottom magnet. So I would say that the like poles, which in these case are N poles, so like poles repel. The top magnet is replaced with a ring made of iron. Explain why the iron sticks to the bottom magnet. So I know that iron is a temporary magnet, so poles are going to be induced on it such that the bottom magnet is going to attract the iron. So I'll just say this, that iron is a temporary magnet, and poles will be induced, or I can say unlike poles will be induced, because I know it's going to be induced magnetism, because I know it's always attractive, and unlike poles will be induced such that the magnet attracts the iron. So that's this. Let's go on to the next part, to another question. So this question is from winter 18, paper 21, question number 6. And again, pertinent to stuff that we've discussed already. So let's have a look at this one. So 6.1 is the view from above of a stationary magnet and a small compass on a lab bench. State the material from which the compass needle is made. Because the compass is always going to retain its magnetism, I infer it's a permanent magnet, hence it's steel. Next part, describe how the small compass is used to plot magnetic field lines in the region surrounding the magnet. So we've talked about this already, that how this happens, and we've also seen the video that described this. So first I would say mark, because I see how this is marked. So this is marked near to the south pole, right? So with the south pole, if I think about it, I can also right now see that the north, which is basically the pointed tip, is pointed towards the south. So how can I make this? Now only this time the change that's going to happen is that I would now make a dot here, and then I would align the dots according to that, right? So this time this is my south pole, because this is also placed close to the south pole. So I would mark at the further end of the needle, which is further away from me, and then I would move the compass and then do everything same as I used to, and that's how I can get the field lines. So I'll say place a dot at the further end of the needle. And also generally, if you think about it, if you say the further end of the needle, then that would work out if you talk about this according to either it being placed near the north pole or the south pole, right? So that's a good thing about writing it like this. And then adjust the compass so that the nearer end is at the dot. Mark at the further end again. Repeat until the other pole is reached. And then join up the dots with a pencil. All right. Next question. An unmagnetized iron bar PQ is placed near to the magnet on the lab bench. 6.2 shows the pole of the magnet and PQ. So this is the magnet. This is moved like this. This is the iron bar. And then the question says this: the iron bar is initially at rest and the magnet is moved to the right very slowly. When the magnet is a short distance from the iron bar moves very quickly to the left towards it. Explain why the iron bar is attracted to the magnet, right? So this says that this iron bar was initially at rest and the magnet is moved to the right, and then the iron bar moves quickly towards the left. So basically it enters the field of the magnet. Explain why the iron bar is attracted to the magnet. Same question based on induced magnetism and how you're going to describe this. So you know that poles are induced on the iron bar. And if I'm told that this is going to be attracted, I can already figure out what the poles are going to be. So for attraction, this must be a north, this must be a south. So I would say the P becomes N, a north pole, and Q becomes a south pole. So unlike poles attract. Right? So unlike poles attract. Now if you look at the mark scheme for this, the examiner also says something like this, that the attraction is greater than the repulsion. That's basically because these are closer together as compared to this arrangement. So this distance is less as compared to this. So some people might also say that the force of attraction is greater than the force of repulsion, but if you've written this, this is also good to go. So that's some of the past paper questions regarding simple magnetism. In the next video, we'll start with electromagnetism.